Good afternoon, everyone, and welcome to Chase Plastics Chase the Knowledge webinar on Polymer Basics. This is the first part of a five-part series we're calling Chase Plastics 101. My name is Sherry Cudd, and I'm the Advertising and Marketing Manager for Chase Plastics. Thank you all for your interest in this webinar and for taking time out of your day to attend. A few housekeeping items before we begin. Everyone except the presenter is on mute and will be for the duration of the webinar, but if you'd like to ask a question, you can do so at any time by typing it in the questions section of your toolbar. If you'd rather ask your question verbally, please raise your hand using the react icon in the toolbar and I will unmute you and call on you to ask your question out loud. If your question does not get answered right away, we will address it at the end of the webinar. You can access and download PDF copies of this presentation, our product line card, our common processing guide, and information on our technical engineering team in the materials section during the presentation. If you are attending live, a certificate of completion and a recording of the webinar will be emailed to you about an hour after the webinar concludes. You will receive a separate email from Andrea with a PDF of her presentation and handouts. We would greatly appreciate it if you could complete the survey at the end so we can improve future webinars for you and cover the topics that interest you most. We encourage you to check out past webinars and recordings in the webinars page of our website at chaseplastics.com/webinars. If you would like a custom Chase the Knowledge presentation given to your organization discussing a specific topic or material, please send an email to your presenter, Andrea Kendrick, or myself. Our entire sales and technical team are always ready to assist with technical issues, material selection, and educating you and your team on products and processes specific to your needs. Future Chase the Knowledge webinar announcements will also appear on this page as they are posted, including links for this five-part series called Chase Plastics 101, where we will discuss polymer basics today, modification, testing, fabrication, and common polymers. You can register for part 2 on understanding polymer modification on June 25th now. You can now subscribe or invite coworkers to subscribe to receive notifications of all future Chase the Knowledge webinars here as well, where you see click here to subscribe. Another great technical resource is the Chase the Knowledge blogs on our website. They can be found at chaseplastics.com/blogs or under the resources tab from the homepage. We recently added a blog on the advantages of peak and extreme and demanding applications. In addition to our presenter, Andrea Kendrick, whom I will introduce in a moment, we also have Jason Merkel, Technical Manager, on hand to answer your questions today. At this point, I'd like to hand it over to our presenter, Andrea Kendrick. Andrea is a technical training engineer with Chase Plastics and has been with us since 2015. She received her bachelor's degree in plastics engineering technology from Ferris State University. For those of you who have attended Chase the Knowledge webinars in the past or contacted our technical engineering team for assistance, you're very familiar with Andrea and the level of expertise she brings to the table. So without further ado, Andrea?
Hey, good afternoon, and welcome to our first part in a five-part series, Chase Plastics 101. This first part is going to be over polymer basics. The other thing that I would note is if you're in front of your computer and you're following along, hopefully, it might not be a bad idea to also have the common processing guide that Sherry referenced open as well. There's a couple slides where I referenced a couple parts of it. It wouldn't be the worst thing to have in front of you as well if you would like to have that open. Okay, so for today, we're going to go over what is a polymer. So we hear the term polymer pretty frequently when we're talking about different plastics. So we're going to go over what that is specifically. Then we're going to go over characteristics of polymers, plastic polymers, obviously specifically. We're going to go over semicrystalline versus amorphous and those differences that make a big difference when you're looking at different polymers. We're going to go over some other classifications, so stuff like your commodity versus engineering versus specialty, and how we would then classify those materials and how they fit in. And then we're going to go over common polymers. So we're going to go over some of the common types and how they fit then into those two different categories, semicrystalline versus amorphous, and then classification, commodity, engineering, specialty. Okay, so what is a polymer? So the term poly means many. So if you have a polygon, it's got many sides. So many is for polymer. And then the mer means units. So the complete definition is going to be that it has many units. So a base cell or a base unit that makes up our plastic polymers is going to be known as a monomer. So if you hear the term monomer, or other variants of it, mono meaning one, again, mer always meaning units. A monomer, which is what's highlighted here in this picture, your two CH bonds, this is going to be an ethylene monomer. Once we have many repeat units of it, it is considered a polymer. And so as you go through and you add more and more of the same monomer, you start getting different variants of the material itself. Again, still the same chemistry, so the C2H4. If you have just a CH4, you have a methane gas, same monomer that we're talking about. Once you get to 8 carbons, now you're in a liquid form. That's going to be your octane gas. Once you get to about 50 carbons, you're in your wax phase, so kind of like your candle waxy type. You can see as the phase of matter is kind of shifting as you have more of these units. And then finally, you get to the point where you're at tens of thousands, hundreds of thousands of these repeat units. Now you're starting to create a polymer. And so as you can see, as it goes up in different, again, matters, you go all the way to your polymer, tons and tons of repeat units. And so all the different building blocks of our plastics have a monomer that it starts with that we repeat many, many times to create our plastic polymers. Okay. So one thing to note is that plastics are polymers. They're a bunch of repeat units, but not every polymer is a plastic. So there are other polymers that exist. DNA is considered a polymer. Proteins are considered polymers. Cellulose considered polymers, and others as well. But just to point out that all plastics are polymers. They're made up of a lot of repeat units, but not all polymers are plastics. Okay, so now we talked about polymer, the term, kind of what it means, why we use it, but then we'll get into now some more of the characteristics of our plastic polymers. So the first thing to note is that plastics are man-made. They're not just out reoccurring in nature and something that we then harness. It's something that we have to be forced into being made. And so we make them via a process called polymerization. I'll go over a couple of the common ones just a little bit later to go over some of the differences. But man-made via polymerization. Then the actual properties then of these materials are going to be determined by 3 main things. Your chemical composition, so what are the monomers and the elements used to make these polymers? Then it gets into the shape of the chains. So are we talking a linear type backbone? Is it branched? Different shapes there. And then your alignment. So how do the chains align near each other, or maybe not so near each other? So that's kind of when we start talking a little more of the semicrystalline versus amorphous realm, and we'll get into that as well. So going into each 3 of them, we'll talk about chemical composition first. So there's quite a bit going on this page, but to point out, you can see the atomic radius. So this is just simply going to be the size of the elements. And so if we're looking at our material PVC, polyvinyl chloride, down here on the bottom left, compared to our polypropylene, bottom right, although the drawing itself, because it is written just small, looks like they are the same, your PVC atom, the chlorine atom that's hanging off of the backbone, is actually quite a bit larger than your CH3 group is going to be. So because it is so large, that pendant group that hangs off, it results in the PVC material not being able to crystallize, meaning it can't get close to the other lines and chains of that polymer. So PVC, again, just having a chlorine atom different than polypropylene, which has just carbon, it's so much larger that it results in the material being an amorphous resin versus being semi-crystalline. There's other things as well. PVC, because of the chlorine atom, also allows for a little bit better chlorine resistance and a few other things. But when we talk about the composition, just comparing these two, that difference in size of the atom that hangs off the backbone makes a large difference in the materials and their properties. And so same with a lot of other stuff as well. So propylene here has the CH3 hanging off the backbone. If we were to go back a couple slides to the ethylene, it doesn't have anything hanging off the backbone. And so all different types of compositions that make a difference. Some materials use different elements as well. Your nylons are going to have nitrogens and they're going to have oxygens on the backbone. And so a lot of different compositions and ways to make these materials. I'm not going to go through them all and give chemistry for all of them, but it makes quite a difference in the performance of the material. Okay, so that's our chemical composition, different elements that are being used, different maybe arrangements of the elements, but overall different elements that are being used. Now we're going to talk about the shape of the chains now. So the best example of that is going to be your polyethylene. So again, we go back 3-4 slides and it's just your CH atoms. And so if we look at the different types of polyethylene, if you're familiar, we've got high density, we've got linear low density and low density, and sometimes we'll throw in a medium density, but really those are going to be kind of your main three, all based off of the C2H4 chemistry. So our chemical composition for those materials are all the same, but the way that they end up branching or not branching starts to make them different. It causes them to have different densities, slightly different performances because of that. So if we look at density, we know that density is mass over volume. If we know that the volume of material that we're looking at or comparing is going to be the same, the mass and how much of those molecules we can shove into that same space will be different. It's why they use the term high density, low density, or linear low. So linear high density, you're going to see there's no branching off of it. And so what it allows it to do is within, again, the same space, it's able, the molecules and the chains are able to get really close to one another. So a lot more mass in that area, resulting in your higher density. Linear low is going to have smaller branches off, and then low density has long branches. So as you can imagine, if it's trying to get really close, the branching on there is going to hold it off and make it difficult for it to tightly pack in there. So your low density has a lot more spacing between your chains, resulting in less mass within the same volume. And so you end up with a low density. So if you compare the actual then density of these materials, a pretty standard range that you're going to find for your high density are going to be between the 0.937-ish range to 0.96 versus your low density, which is in the 9.1 to 9.2 range. So again, exact same chemistry, your CH2 groups, two of them, but whether it branches or not, the shape of those chains now are dictating its density as well as some of its performance as well. As you can imagine, your high density gets a little closer, maybe a little stiffer, not as good impact type of stuff. So other properties are also affected as well. But all this to say, chemistry makes a big difference. If the chemistry is the same, but the shape of our chains is different, it also then affects how the material will perform or what type of properties it will have. Okay. And then lastly, we have what we call the alignment of the chains. And so the chemistry is the same, or excuse me, if you have your chemistry is different or your chains are different, the last one is going to be how they then align themselves within the matrix of the material. And so our overall arching polymers, we have plastics is what we're referring to. Then we have two types within plastics. You're going to have your thermosets. So these are going to be materials, and I don't have a slide to spend a ton of time on it, but thermosets are going to be your materials that go through a chemical change when they are processed. So these are going to be your rubber materials. These are going to be your epoxies, stuff like that, where they're going to go through a curing process and it's going to create those bonds there. They're not easy to recycle. The analogy that's always used is you're baking a cake. You have all the ingredients that go into it. You bake a cake. Now you've created something new, you've changed, it goes through the chemical change. I can't go back and get all of the original ingredients that I started with. Versus your thermoplastics, which are more like ice cubes. So you have an ice cube, it melts, it's still water. If I freeze it again, it's still water, it's still now in an ice cube. So I can recycle them a lot easier. These are going to be the materials that we would then sell and the ones that we will talk about for the rest of this presentation. But thermoset, again, your rubber type material. Think of your windshield wiper blade. Those are typically made out of EPDM, or your tires are made out of different types of rubber. Those are all going to be thermoset materials. And then you have amorphous materials, which falls under thermoplastics, which is going to be stuff like your ABS or an SAN. And then your semi-crystalline materials, which are going to be your different types of nylons. So how they then align themselves, semi-crystalline versus amorphous, we will spend a little bit of time going over that in the next couple slides. Okay, so again, focusing on thermoplastics, that's what we do here. That's what I'm assuming most everybody listening in is what they process. So that's where we're going to spend our time, right? So within thermoplastics, we have semi-crystalline materials and we have amorphous materials. Semi-crystalline are named that because they're not fully crystalline. And so they have dense, tightly packed regions known as crystals. So if you look at this picture, these little squiggly lines that are a little more organized, a little bit closer together in pink, those are going to be your crystal regions. Called semi, again, because they're not fully crystalline. Generally, you're between about the 30 to 70-ish range is pretty standard for how many the crystal region amount you'll have. Then you have amorphous materials. And so amorphous, A means without, A or an means without, and then morphous means structure. So defined, it means without structure. Your amorphous materials don't have those tightly packed crystal regions. It's a very random structure, if you will. And so, and then because of that, because of the way those then will align themselves, it plays a part into their performance and what is expected of them. And so we will spend the next few slides talking about that specifically. Okay. So semi-crystalline materials, again, they have areas of tightly packed ordered regions. So highly ordered structure, they have their crystal regions. And so what typically happens then is they are typically opaque. There are some materials where they might have crystallinity to them and they can be transparent, but generally speaking, they tend to be opaque. We do not see through them. Generally, the crystal regions don't allow the light through super well. So more crystallinity it has or the more crystal regions it has, it doesn't want to allow the light through. So they're generally not transparent. They're almost always opaque. Okay. Because of those crystal regions, they have what's known as a TM, which we'll talk about in a further slide, but a melting temperature. That's the temperature at which your crystal regions will break apart. So because of that, they have a very distinct processing temperature you're going to aim for. So we call it a sharp melting point. So we want to hit that TM, allow the crystals to pull apart far enough to be processed. So you'll hear the term a sharp melting point when you talk about your semi-crystalline. A smaller processing window in terms of heat as well, and we'll show that also. Shrinks more. So because of those crystal regions that are really tightly packed, we need to get them to expand out so that way they can flow by each other. We've got to basically untangle those tight regions so we can get the material to flow. And so when it starts to cool, they want to go back to those tight, highly organized, tight crystal regions. And so they shrink more to try to get back to that. And so when you're talking designing a tool, we want to know if we're looking at a semi-crystalline or amorphous material because it's going to dictate what type of shrinkage we're going to be looking at using. Your semi-crystalline material, they're going to shrink more. And so a typical range for them, although it's highly dependent on the material itself, and then also if it's filled or whatnot, but a real general rule of thumb is going to be from 10 to 20 thou inch per inch, or if you use percentage as an easier way to picture it or understand it, 1 to 2% is pretty standard. And again, it comes down to the material, it comes down to if it's filled with anything or not, but that's a general range that we can use for it that tends to encapsulate most of those materials. The other thing that's nice about the crystal regions is not only are they stopping the light, so You typically have your opaque materials, but it also tends to stop chemicals from penetrating. And so you generally find you have much, much better chemical resistance with semi-crystalline materials. And so there are some highly specialized materials that are amorphous that have good chemical resistance, but generally speaking, if you're looking for that chemical resistance, you're looking for a semi-crystalline material. And then the crystal regions also allow for better wear and fatigue performance as well. So if you're using anything that needs any type of wear and friction performance, maybe it's a gear, maybe it's wearing on something, you're going to find that your semi-crystalline materials are going to be the ones that you're going to look to. So in those types of applications, you'll almost always hear acetal and nylon be recommended. Those are going to be two semi-crystalline materials that are used commonly in those types of applications. Okay, and then on the flip side is going to be your amorphous material. Again, no structure. They don't have those crystal regions. And so random structure, because they don't have the crystal regions to block the light, they are typically transparent. There are some caveats to that. Materials like ABS, because of the butadiene, are not transparent. But if you remove the butadiene and have SAN, it is transparent. So most of the materials are going to be transparent. Think of polycarbonate, acrylic, polystyrene, clear materials, amorphous. They have a gradual softening. So compared to the sharp melt point that you'll have out of your semi-crystalline, they have what we'll call a gradual softening. So they just slowly move apart and expand just a little bit, and then we are able to process it. Because of that, you generally then get your wider processing window. So there's a wider range of temperatures that can be utilized to process. And again, we'll show that on a slide. They shrink less, so they don't have to expand as much. They're not trying to fight crystal regions to break them apart to get them to flow. So they don't expand as much, so they shrink a lot less when they go to cool. And so general range for them is going to be 3 to 7 thou or 0.3 to 0.7 for shrinkage. So it's very, very common, and it's a pretty tight window compared to the larger difference you have with semi-crystalline, a much tighter window. So generally speaking, if you tell me you're working with a certain material, I know it's amorphous, I'm somewhere in that range for my shrinkage. Again, a little bit of change. If we have it filled with something, that might change a little bit, but generally speaking, 3 to 7 thou is going to be where we're at. Because of that low shrinkage, you're going to have less variation. You're also then going to have better dimensional control, and you're going to have less chance of it warping. So warping tends to happen when you have shrink that's happening, and you have differential shrink, little different directions, anisotropic shrink, if we're using that term. You have a lot less of that typically with your amorphous materials. So generally you have a higher resistance to it warping, better dimensional control. And I have, again, some data on that as well to show it. But holding tighter tolerances, and you have less chance of warping with your amorphous materials. Okay, so I mentioned some of the thermal transitions just a little bit when I mentioned TM. Now we're going to talk about TG a little bit. It's kind of a lot to take in, but your glass transition temperature, you'll see them on some materials. If you look on data sheets, they'll tell you the TG of the material. TG, what happens is when you start to warm up to it, or you're starting to get to it or go beyond the glass transition temperature of the material, there's enough thermal energy there now that the molecules can start to move. And so within the material, if the molecules are starting to move, they're not holding their rigid structure anymore. And so the term, or the way that they'll describe it, is they call it glassy if you're below the TG, because it's very rigid, it's very strong, it feels more like glass. Everyone can picture glass, very strong, very stiff. When you go above the TG, it's considered the rubbery phase of it. It feels more soft, more flexible. It's able to move a lot easier. And so we want to know where our TGs are for our material when we're designing, and to understand overall the thermal performance of the material. Both semi-crystalline and amorphous materials will have TGs, will have glass transition temperatures. We again want to know that, as you can see kind of in the charts that are graphed. You can see modulus, which would be your stiffness versus your temperature. When you hit the glass transition temperature of your amorphous materials, because you don't have any crystal regions there to hold any type of structure, you're going to lose all of its function. So it's not holding any structure, it's not holding any stiffness and strength any longer. So TG is a really important value to understand for your amorphous materials, because the term that we use is that the material is useless above its TG if it is amorphous. And that's shown, I think, fairly clearly in your chart here. Again, stiffness versus temperature. Once you hit the TG of that material, you lose all stiffness. It's gone. So the amorphous material is not holding up anymore. It's not doing its job. If you're using this for some type of structural component, it's not a structural component anymore. You're above its TG, its glass transition temperature, and so it's no longer useful. Semicrystalline materials, on the other hand, have a TM, which we'll get to on the next slide. And so you'll still lose, because the semi part means that the other portion of your semicrystalline material is amorphous in structure. So if you have a material that's 30% crystalline, you have 70% that's still amorphous. And so when you hit that TG, you're going to lose some of your stiffness and strength. And so you maintain some of it, but you're still going to lose some of it. And so we have to determine, if we're designing something, how much loss can we take? Could we lose half of its stiffness and have it still perform okay? Is that not acceptable? It's just one of those things where knowing these temperatures and their performance is really helpful when we're designing for parts that are going to see elevated temperatures. So in this case, we're looking at a PBT. You can see stiffness really good. We hit our TG. The amorphous materials or section is starting to move. You're losing some of your stiffness and strength. It's still maintaining some, but you're losing some of it. So again, we want to make sure we understand these when we design for parts that are going to see elevated temperatures. It's one of those things we want to make sure we understand. And then here, which we'll get to the next slide, is going to be the TM, your melting temperature of the material. Okay, so your melting temperature, because of those crystal regions, you have to have more thermal energy than is required to move the amorphous sections. And so your melting temperature, TM, is the temperature at which the semicrystalline materials, there's enough thermal energy to break apart those crystal regions. So what happens is we hit that. Now there's no more structure and strength to our semicrystalline materials. Now we can get them to flow, and now we can process them. So good to understand your TMs and your TGs from a design perspective if we're talking about thermal points. And then also it's what's used to help determine how we're going to process it. So all of the processing temperatures that are recommended from suppliers and manufacturers, those are based on understanding these thermal points of these materials. We can't mold a semicrystalline material if we're under its TM. It still has those crystal regions that are not trying to flow. And so potentially, if you've ever ran a material too cold and you still had portions of it that were not melted, maybe that's what you were getting. You had some crystal regions that hadn't fully broken apart yet because you weren't at that temperature. So again, TG for your amorphous, because it doesn't have crystal regions, it does not have a TM, and then your semicrystalline materials, TG and a TM. And so if we graph that out on what looks like a DSC curve, so if you were with me on my last presentation where we went over DSC curves, you can see kind of heat in, heat out. All of this, though, to say we have our melting temperature here, TM, for our semicrystalline, and then we have the temperature at which the material is going to degrade. So you can see our processing window is much smaller than what you could get away with an amorphous material. So starting the TG, it's molecular movement. We're able to move a little bit. And then we get to degradation, much wider processing window for amorphous materials. So when we give you a recommendation for either of these, but specifically your semicrystalline materials, if we're saying, hey, here's the processing temperature for this material, it's a good idea to be pretty dang close to it, because if you go much hotter, you're introducing a little more shear heat, whatever it may be, you're getting real close to degrading the material. And so when we say a sharp melting point, here it is, there's your processing window, versus a gradual softening that we can then process within. And so in this point would be the idea, if you happen to have your processing, the processing guide in front of you, few things that are being shown on here. One would be your processing temperatures. So this would be your melt temperatures here. Again, we don't give the degradation temperature to show how close it is, but know that for those semicrystalline, really try to aim for that. You go much further, you're going to degrade it pretty quickly. And then to show the shrinkage information. So we said semicrystalline 10 to 20 thou inch per inch, and your amorphous 3 to 7 thou. So if we looked at ABS, we know, or at least know by now, I've said it a couple times, right? Amorphous, it's an amorphous material. So they're 4 to 7 thou for ABS and FRABS and ASA. And then if we're looking down here at the different nylons, we're at 18 to 22 thou, 11 to 15, and 10 to 14. So a lot bigger difference within it. So changing between amorphous materials would be a little easier from a shrink perspective, because again, they all tend to fall in that closer range. Your semi-crystalline materials have a larger range, and even within the family of semi-crystalline materials, a larger variance between them. And so all things that we want to make sure we're aware of. It's also why we like to try where we're able to help out with any type of design or material recommendation in the beginning. Because if you go through all this process, you cut steel, you're trying to make parts, and then you find, oh, it's got chemical exposure, or it's got something where maybe it's a wear part now, or we didn't pay as much attention to the fact it was going to need to be a wear part. Well, if you designed it for an amorphous material and you cut it for shrink for an amorphous material, but you really need a semi-crystalline material for its performance, well, now we have a potential problem, because we might not be able to cut away or cut where we need to. And now we're trying to fit a solution into a mold that wasn't really made for that type of material. So where it makes sense, knowing what material is going to work best for the end application, and then cutting steel for it, or aluminum, if you're going to do a prototype, right? It's really important to know these things. It makes a huge difference, one, between performance and then also for your shrinkage. Okay, and then some additional data to go with that, as I mentioned, better dimensional stability and control for your amorphous material. So to show that, for those that have seen it or have it, your standard practices for dimensional tolerancing for these materials. So SPI has a bunch of guides for different standard materials, and they go through what's considered acceptable ranges and tolerances for different dimensions. And so if you look at the one, I just picked two random ones, a semi-crystalline amorphous, ABS picked randomly. And so if you're looking at a fine or tighter tolerance control, plus or minus 7 thou, versus a 12 thou commercial, plus or minus. Then if we look at nylon, which is very broad for nylon, mind you, there are different nylons. Some are going to shrink a little more. A nylon 4-6 is about 70% crystallinity, so it's going to shrink a little bit more, versus a 6-6 shrinks a little bit more than a 6. And so grain of salt, but you look at the fine, you're at plus or minus 9 thou. So you're already 2 thou different than an ABS, and then commercial 13 thou. So within a semi-crystalline versus amorphous, you can see expectations are different for holding different tolerances because of the way that it shrinks between amorphous and semi-crystalline. And there's other ones as well, of course. These are just ABS and nylon, but they've got other materials as well that will show the same pattern. If it's amorphous, you're going to be able to hold tighter tolerances with it versus a semi-crystalline material. Okay, so now we talked about kind of general characteristics. We talked about our chemical composition a little bit. We talked a little bit about our the shape of our chains, if it was branched or linear. And there's other materials also that fall into that. You might hear the term branched or linear PPS. And so, polyethylene is not the only one that you'll see described that way. And then finally, our amorphous versus semi-crystalline for how the chains align themselves within the molecule. But another way to characterize or group our materials is going to have to do with how they are polymerized. So we said that polymers are man-made. They don't occur in nature. We have to force them to be made. And there's two main ways that that's done. It's done via addition polymerization, and it's done via condensation polymerization. So what's unique about your condensation is that water is a byproduct of that polymerization process. So water is given off when the polymer is being made. This is important to note because if we're giving off the water, if we put the water back in and a lot of heat, we can cause the process to go in the opposite direction. So known as hydrolysis, if we put the water back in, elevated temperature, we're going to now start to break the chains apart instead of creating or extending the chains like you would with the polymerization process. So with that, the materials that are made via condensation polymerization are going to be materials that we are concerned about moisture when we go to process them. So what does that look like? Again, our handy processing guide. And so we have them grouped by hygroscopic or non-hygroscopic. So your hygroscopic materials are going to be ones that will take in moisture, they'll pick up moisture. And so if they're going to pick up a lot of moisture, if you don't dry these materials, you'll cause the polymerization process to go in reverse. It'll go through hydrolysis and we will start cutting up the chains. And so if you are familiar with or have ran nylon at any given time, you've probably experienced it at some point. And so when we recommend a drying time, a drying temperature, and a max moisture content, that's because we're trying really hard to make sure when you process the material, you're not degrading it and cutting up those chains. And so the most common ones in here are going to be your nylons. They're the ones most commonly affected by this. They pick up moisture nicely. But a lot of other materials as well. ABS, polycarbonate. If you've ran polycarbonate that wasn't dry, maybe you're getting the splay and the little bubbles throughout the clear part. Your nylon, you'll get your splay. And I have a picture on the next slide to show that. But all this to say, an additional classification for your materials. Non-hygroscopic materials are ones that are not going to pick up the moisture and pull them into their matrix. And so, but that's not to say that if it's moving from different climates, you might end up with some surface moisture. So although the moisture or water might not go into the pellet itself, it might sit on the surface, which could potentially cause some issues. Not as dramatically as if a material is sitting open and it's allowed to just suck up the moisture from the air, and then you have a wet material that you're trying to run. But keep that in mind. So the materials grouped under non-hygroscopic, so your propylenes, your ethylenes, those types of materials that were made via addition polymerization, they're not as heavily affected by the moisture versus your nylons, your polyesters, polycarbonates. So when we give a temperature and a drying time, it's really in hopes that we're drying it to an appropriate level, and so we don't have issues when we go to run the parts. Okay. And so if you've not seen it, that's awesome. But if you have not dried a material well enough before, you'll end up getting what's known as splay, or maybe silver streaking, whatever you might call it. But you can see on the surface, you've got that defect there. This is from a material that was not dried, had a nylon component, and it was not dried appropriately. So you can see that there's a surface defect. And the issue too is that the surface defect you can also see, but you're also then likely affecting the viscosity of the material. You could be affecting its performance as well as the way that it looks. And so if you have a part that has a requirement to perform a certain way, if we degrade it, not only will it look bad, but then it's also not going to perform well. So with our polymers, if we need to dry it, we need to dry it. We want to make sure that we're drying it appropriately. And so we run into a lot of issues where, drying is not done, and then you end up with subpar parts and material appearance. And then you can see the other one. The lighting's kind of funny. It's not actually gray. It is black, but the lighting is kind of funny. But you can see that the material was dried correctly, and you don't have that issue. And so we want to make sure we're drying it. So one, it looks great and also performs the way that it is supposed to. So hygroscopic versus non-amorphous versus semicrystalline. And then lastly, another way you might see them described or classified is going to be commodity, engineering, and specialty polymers. Some people will use different terms. Maybe you'll see a general, then you'll see an engineering, then you'll see they use other terms as well. These are the terms we tend to use. We feel like they make the most sense, right? But these are going to be the ones you see. So from a material pyramid perspective and grouping of those, your commodity materials are going to be stuff that are lower cost, typically, generally sub $2 or $1, so not super expensive, lower performance. They're not going to perform at the same level of heat or stiffness and strength requirement that you'll get with other materials. And they're typically bought in larger quantities. That's not to say that, there's not some programs here and there where you might need a box or two of these types of materials. But generally speaking, companies are buying truckloads or rail cars of propylene and they're making, or ethylene and they're making totes out of it, or they're making, plant pots or whatever it may be. We're doing it in a very large quantity typically. Then you have your engineering materials. So this is going to be a step up in your temperature performance range. So maybe propylenes, ethylenes, maybe you're in the 100 C-ish range that we might be able to perform in, not super highly engineered parts are going to be made out of that typically. Then we move to engineering. So these are going to be your nylons, your acetals, a little more everyday, but still they're a little more specialized. They have higher temperature performance, better stiffness and strength, or maybe some other unique performance feature. So ABS with the butadiene, good cold temperature impact. Your acrylics got good UV performance. Acetal and nylons, great for wear and friction performance. So maybe an additional feature that makes them a little more unique and allows them to perform at a higher level. So we would consider these more moderate cost, moderate performance, and generally bought in more moderate quantities. Maybe half a truck, maybe a couple boxes here and there, all dependent, of course, on the program, the part, whatever it may be. But generally, you buy them not as large of quantities typically for them. Whereas your commodities, maybe you have a silo if you have a large program for it. You might get a silo for engineering materials, but generally not. And then you have top of the pyramid. It's going to be your specialty, highly engineered products that have really unique features or performance that put them at the very top. So stuff like PEEK or PPS would also be on the semicrystalline side, high temperature, really great chemical resistance performance. Then you have PEI, sulfones. They're clear, high temperature, amorphous materials, good chemical resistance, which a little different than your standard amorphous materials, but highly specialized for the types of applications they can be used into. They're typically high cost. We're talking 10, 20 upwards for some of these materials, dollars per pound, really high performance. Certain design features or certain performance features these materials offer that are super unique to what they do. And they're typically bought generally in a lot smaller quantities. We will, of course, never be mad if they are bought in larger quantities, but generally programs don't require, a full truckload of a PEI type material. And so you buy them in smaller quantities. They're very specialized and very unique. And so with these materials, then when it comes to picking a material to do something, once you're kind of in the engineering plus, it's one of those things where it might take a few additional conversations to make sure we understand exactly what performance features are needed. So then we can start to pick the materials that will best suit that performance. And so we tend to, at Chase specifically, we do tend to focus on our engineering and specialty, but to point out that they are all within that range. And then amorphous and semicrystalline, as you can see on the two different sides, are also specified there. The other way to do it too, to tell, or if you're unsure and you're looking at a material and you're like, I don't know where this falls. If they have it and it's unfilled, you could look at a shrinkage value. That might help you. And so there's some ways to figure that out or to look at that. And then worst case scenario, you can always ask. We're more than happy to help. But this would be the final way that we would tend to categorize our materials. So composition, how they work, amorphous versus semicrystalline, and then finally the last one, your commodity versus engineering versus specialty. And so with that, that is what I had for you guys today.
Awesome. Thank you, Andrea, for your comprehensive presentation as always. At this time, if you have any questions, please type them into the questions section or raise your hand. I see some people raising their hands and a bunch of clapping. Thank you, Andrea, for a great presentation. Please type them in the questions section or raise your hand and I will unmute your microphone. We do have Jason Merkel, our technical manager, on hand today to assist Andrea with questions. So as a reminder, as you type your questions, please remember to complete the survey at the end of the webinar. Your responses do help shape future Chase the Knowledge webinars. And as always, we welcome your feedback. Also, please be sure to check out our blog page, chaseplastics.com/blogs. And past webinar recordings that you can watch at your leisure and future webinar announcements, including the rest of this 5-part series will be on chaseplastics.com/webinars, and you can register for the June one today. If you'd like to have a custom Chase the Knowledge topic presented to your organization, please reach out to Andrea or myself, and we can help you set that up. So questions, Jason, I'll hand it over to you. It looks like we have one in the box. I'll see if we have any hands raised.
Thanks, Sherry. Andrea, as Sherry said, just one question for now. We'll see if any others trickle in. But first question is it possible to over dry materials?
Yes, it's more common with nylon materials. So when you run nylon materials, the moisture in them, it helps to plasticize it a little bit. It helps with its flow and its viscosity. And so nylons most commonly can be over dried. So if you look at the guide or you have the guide open in front of you, you'll see that there's a range then instead of a max moisture. And so again, nylon being the most common. The overarching question is if you dry it at too high a temperature or dry it for too long, you can technically over dry anything because it shouldn't be in a dryer for that long or that hot if you're doing either of those things. But nylon is the most common one for that. Generally, there's a range between 0.05 to 0.2 generally is where we want to see that moisture. And so it will still run nicely. We don't dry it completely out so it becomes brittle and then doesn't want to flow super easily. So yes, the answer is yes, you can over dry it. There's a few caveats to it, but generally, yes, you can definitely over dry it.
Awesome. Thanks, Andrea. We did have one other one come in just now. First of all, congratulating you on the excellent presentation. But
Thank you.
customers asking if they wanted to do a tri-extrusion of LDPE, PET, and then LDPE again. How do we ensure the 3 layers stick to each other?
That's a good question. I don't have an answer for that one. I would imagine don't they make tying layers or tying materials to help tie them together? They're either going to want
Yeah.
to stick together or they're not. And then I would imagine they do tie layers for ones that don't want to, but I'm not as familiar with that.
I'm in the same boat. I haven't seen PET and LDPE specifically bond together in a tri-extrusion. Not saying that it can't, but we'd have to research if there are specific grades that would be more miscible than others. So sorry to not completely answer your question there, but we can definitely look into it and get back to you after this discussion. But we'll take a little research on our end as well.
Jason, we have a hand raised. If you don't mind, I'll unmute
Yeah.
Paul Nosek. Paul, let me unmute you here, and then you can just speak your question to us. Let's find you here. Okay, Paul, I'm going to unmute you.
All right. Better?
Hi, Paul. Yep, we can hear you.
Hi. Great. Going back to drying, I have a question. What happens when you over-dry material? What are visible effects? And I'm specifically want to know about Altem.
If you over dry Ultem,
Yes.
so it would come down to if you did it for too long or too hot, the first things that could happen is you might burn some material. In some cases, and I don't know if this is for Ultem specifically, but additives and stuff that are in it, releases, things that would be in your material, you can degrade them a little bit sooner typically than you would the base material. And so you might end up degrading the stuff that's in it. And that could show itself in a few different forms. I've not dealt with someone over drying Ultem specifically, but yeah, you could end up burning it. You can end up having the additives degraded, so then it doesn't process as well. And then I don't know, Jason, I
Is
don't know
it
if you've.
visible?
But
Is it something visible on the surface of the part?
it could be. It could be. That's the answer. If it's really, really bad and you burn it and stuff, you're gonna have a visual, you'll see it visually. If you're degrading the additives, you might see that come up as it could come up as splay, or it could show in other ways. Again, I've not ran into over drying the Ultem. Jason, maybe you have, but it's
Yeah,
possible.
no,
It really comes down to the degree.
yeah. Typically, we would expect that if you are over drying all timber, leaving it in the dryer long enough to degrade, whether that be due to prolonged temperature or prolonged time, we would expect to see something on the surface of the polymer in terms of oxidation, so dark marks, swirling, something along those lines. Now, if it's very lightly over dried, then you wouldn't always necessarily see it, but we would expect some sort of variance in the performance properties of the parts as well. So again, with Ultem
Is the
being
moisture
at
test will show?
sorry,
Is the moisture test will show any of this over drying situation? It like the moisture content will be extremely low, or it doesn't really show anything.
I mean, you have to get Ultem pretty low in moisture content in general to avoid aesthetic
Below
issues.
0.2. Yeah.
0.02%, right?
Yep.
So
Yep.
really, it's hard to get a whole lot drier than that. So the issue with over drying, so to speak, Ultem, maybe it's a misnomer. You're not actually over drying it because you can't get it theoretically much drier than that. It would be more your starting oxidation of thermal degradation of the polymer. So it's not the dryness that becomes the problem, it's that you're actually starting to break the polymer down due to prolonged time in the dryer. So no
So
is a
one
short
more
answer. You could
question
the moisture
about
reading would
that.
not necessarily indicate it. Sorry.
Okay. If there would be any visible changes in viscosity of material if it's over dry?
Hard to say. I'd have to check. I mean, again, we rarely see over drying issues with Ultem, so we're speaking a little anecdotally here.
Yeah, I also didn't experience over drying, but we have a particular issue with some kind of product, and everybody's telling me that, well, maybe it's over dry, and I don't see why and how. But I guess that's proved my point. So thank you.
No problem. I think in general, as long as you're reaching the adequate drying temperature, that 4 to 6 hours, depending on the grade of Ultem, is typically sufficient. Stretching that up to maybe 10 hours on a case by case basis, only if the material's not seeming to be dry enough yet, would be within the realm of what we would expect to see. Going much beyond that, I think you're at risk of starting to break down the polymer. So we can try to get more specifics based on the resin type that you're specifically using and talk with Savik about it as well. But that's about the extent of what we've seen so far.
But it would definitely not create any void in the material or bubbles.
Only if you were somehow changing the viscosity of the material.
So viscosity can do that, but not over drying.
Well, if you over dry it to the degree of degrading the material, then yes, you have a chance of lowering the viscosity via shorter polymer chains.
Okay.
But that would be extremely uncommon for Ultem.
Yeah, sometimes strange things are happening. So
I understand.
Good
We'd
to
be
know.
happy to discuss it more offline as well, get some specifics on the part and what you're seeing, and try to triage from there.
Yeah, I appreciate it. Thank you.
No problem.
That's all my
Jason,
questions.
we have one more hand up for David. Kevin Dessa. Kevin, I'm going to unmute you if you want to go ahead and ask your question.
Yeah, this is not a question, it's more a comment based on what the previous gentleman was asking about. And it's just take it with a grain of salt. I'm not talking about Ultem specifically, but I've been involved in several projects where I'm going to expand the discussion to over processing. And yeah, if you're over processing, that being over drying, or putting too much shear into the product, or too much residence time in the injection molding unit, etc., it could result in defects that you can't really see on a finished part. I've had this happen where we have parts cracking at assembly or breaking or falling apart in the field, etc. We trace it back to it depends on the process. So it really is an investigation each time. It could be from too much high injection speed, where a manufacturer is trying to inject it too quickly and it's creating a lot of heat buildup and shear inside the system. I think the nozzle, I don't know, might be using the wrong term there, which results in a degradation of the polymer. Over drying can, I'm not gonna say if it is or is not. I mean, it can. It's a potential. But one tool we've used to help our suppliers is we ask them to have it either run themselves. If they can't run it in house, they do it outside a melt flow index reading, temperature, melt flow MFR tests, or intrinsic viscosity, depending on the material they're testing and which test applies. They know their material better than we do. But we ask them to run it. If you see an increase in MFR or a decrease in viscosity, significant decrease in viscosity or increase in melt flow rate, it indicates that you've broken down the polymer. So that might be something that can help you rule in or rule out a root cause. And then on a finished part versus the raw material, and then you can trace it back and get material from the hopper, material from coming out of the injection unit, things like that. You can try and trace it back to where that breakdown is coming from.
For sure. Yeah, thank you for that. Yeah, we ask a lot of questions when people come to us and they say, "Hey, we've got some issues. The parts are not performing the way that we expected them to," and we tend to come with a lot of questions because you're right, it can come from any number of places. Maybe the gate is too small and it's introducing too much shear. Maybe the barrel is too big for the part that you're making and the residence time is too long. So there's a lot that could really go into it. It's like you said, quite an investigation. And so we tend to ask a lot of questions. Not everyone loves all of the questions that are asked, right? But to get to
Yeah,
the
yeah.
bottom of what's happening, we need to figure out where potentially within the process it could be an issue. And then if you get to the point where we're not necessarily finding that, then sure, there's the potential the material could be an issue. So it's very much an entire
Yeah,
investigation to find it.
my experience is the worst thing you can do is go back to the previous one and say, well, last time this happened to me was over drying, so it's got to be that again. Um, so could it be over drying this time? Yes, but could it be something else next time? Potentially. So you just want to ask those investigatory questions. I'm not telling you, it's more a comment for the previous um, person.
For sure. We appreciate that.
Anyway, thank you.
Okay, Jason, I think we're done with hands raised if you want to go back to the typed questions.
Absolutely. All right, Andrea, would you explain how glass affects plastics?
Yes, I will actually, on the next one, I believe we talk about reinforcements as well. And I did a whole presentation on reinforcements. But a very nice quick answer would be glass adds to your stiffness and strength performance of the material. On the flip side, it typically then tends to decrease your elongation and your impact performance. And so if the idea if you're making some type of structural component, whatever it may be, and you need better stiffness and strength performance out of it, you can add a little glass. The other flip side of that as well is going to be that it affects your shrinkage. And so the material itself is what wants to shrink if there is glass in the way, specifically in your flow direction. As the glass lines up, it's not going to want to shrink in that direction as much as it will shrink in the cross flow direction. So if you're looking at a data sheet and it has shrinkage values, it's a glass filled product, If it has both flow and cross flow, you'll find that your flow direction will shrink a little less versus your cross flow. What then that causes is differential shrink. As I mentioned kind of briefly, we talked about warp. It causes a higher likelihood of warp. And so benefit being you get your stronger and stiffer product if you need it, but then we also need to be cautious of the fact that it's going to shrink a little different, and we have introduced a variable that can increase our chance of warping as well. So quick, brief answer to that, but there's a bunch behind it as well, and we've done some other presentations on it specifically.
Rick, I see your follow-up here to the question about the LDPE and PET sandwich co-extrusion. We'll get with you after this call with some answers, so more to come on that. Next question, Andrea. Is it possible to overdry material if it's in the recommended temperature range?
Temperature range would be fine. The issue would be if you left it in there for too long. So the couple variables on your drying would be the time and the temperature. So you can dry your material at the right temperature, but if you leave it in over the weekend, there's potential you over dried it, potential you could be degrading it, whatever it may be, because you're doing it for an extended period of time that's unnecessary. And so, sometimes we'll be told, yeah, we'll just throw it in, we'll dry it over the weekend. That's not always the best option. And in some cases, if it's a requirement or you have to do it in some variant of that way, we might recommend that maybe we lower the temperature a little bit. So then it's not being exposed to that higher temperature for that extended period of time. So there's a few different variables that can cause it. Temperature being too hot, or even if it's the right temperature, if you do it for too long, it can be over dried.
Awesome. Thank you. Next question. Are hybrid materials considered amorphous or semicrystalline? For example, PC-PVT blend.
Great question. What ends up happening when you blend an amorphous and a semicrystalline material is you end up with performance features of both and somewhere kind of in between for them. So stuff like your PC-PVT, if the PVT is working from maybe a chemical perspective, or maybe it's got electrical properties we're concerned with, or whatever it may be that we picked the PVT for, but maybe it's shrinking too much, maybe it's warping too much, maybe it's glass filled and it's warping too much. The introduction of the polycarbonate that doesn't shrink as much, taking up some of the space within that matrix as a blend now, will lower its shrinkage, and then therefore lowering the likelihood of warp. And so it's actually really common for materials like that, for PVT, especially glass filled, to add in PC or to add in ASA that's amorphous in nature to combat your shrinkage and warp issues that you may have. And so the overall classification is difficult. You wouldn't necessarily call it one versus the other because it's a blend of both, an amorphous and a semicrystalline. And we have other stuff like that too. PPE and PA, so your Neural GTX type products, same thing, where you'd have a blend of an amorphous and a semicrystalline. And so you end up with performance in between. And so we wouldn't classify it one versus the other necessarily. It would be a little bit of both. It's a blend.
Alrighty, next question. How many plastics are there? Hundreds, thousands, millions? And are new plastics being created / discovered, or are we mainly dealing with a finite set of plastics now?
Sure. Great question. The amount and types of plastics, 20, 30, not sure. There's not necessarily new types of plastics being developed or discovered. Generally, it's variants of that type. And so you've got your nylons, and they've got so many different types: 6, 6, 6, 10, 5, 6, 10, 10, 11. Then you start putting in aromatic acids and you've got PPAs. So within the actual base type of materials, you've got maybe 10, 20, 30-ish, not so many, but the ability to modify them, add stuff to them, change them slightly, blend them, co-polymerize them. We're talking at Chase within our system, we've got over 40,000 grades of material. And so there are so many options available. But the actual base material itself, there's not, thousands of options.
Thank you, Andrea.
Mm-hmm.
On slide 12, what is HDC and HDH on the PE type chart?
So that would be homopolymer and copolymer of high density. Your crate and paled grades, it's just a type of high density. When you get more into specifics or commonly used high density polyethylene with very specific intention for certain applications, one matters versus the other, and your density difference matters versus the other. So it is called out in some of your grades. You'll see that it calls out a homopolymer versus a copolymer high density. But in a lot of cases, it doesn't necessarily matter. You can use one or the other, but it is a slight difference. Yeah.
Let's see here. Can you overview polycarbonate copolymers in regard to crystalline and amorphous classification?
Polycarbonate copolymers, is that what was asked?
Correct.
So most of the copolymers are going to be amorphous still. And so it's polycarbonate on the backbone, which is going to be your amorphous. And then depending on the copolymer type, you add different stuff into it. So if we're talking like the EXL grades, there's siloxane in there. If you're talking about the SLX, they have ITR. And so, but generally speaking, they're all amorphous. They just have a little something added to their backbone, which makes them a little unique. There are some grades, like some of the medical grades, that are a blend with a semicrystalline material. So they'd be considered a blend, amorphous, and a little bit of semicrystalline in there. So it really comes down to the grade, but the vast majority of them are going to be amorphous materials based on the polycarbonate being the backbone.
All right, I think we got through all the questions. Jason, do you see any that oh, maybe one more just popped up from Elizabeth.
Question is, how do you distinguish between silver streaking and pigment not mixing correctly?
So typically your silver streaking or splay is going to be, it's from moisture. And so generally speaking, it's going to be most common to see, you're going to see it pretty commonly in, you could see it in any of the colors. And it looks like, go back to the slide for it, I suppose. Where you can kind of see it has this kind of unique pattern in the flow and all that. Your color not mixing tends to have a little more of a swirling effect, like it's trying to mix, versus looking kind of like that. The way they look is just a little different. You can kind of tell that the colors, and it could be that the part is expected to be, maybe you're mixing in orange and you expect the whole part to be that nice, maybe it's the high voltage orange, right? You expect it to be all across that nice orange color. Maybe it's a little bit lighter. Maybe you're seeing some swirling somewhere else because the color's not mixing in as well. Generally, visually, you can see the difference. I don't have a part or a picture with colored swirled, but it will look a little different.
Yeah, I think the name of silver streaking helps a little bit here, that with silver streaking or even splay, it tends to be that whitish or silvery more appearance, where pigment not mixing tends to be, the color differences is that whatever the natural version of the base resin is comes to the surface a little more rather than being kind of that silvery whitish, unless the base polymer itself is very white. There's a few other things we can look at. Most of the time, splay and silver streaking has kind of that rounded teardrop shape that a lot of times goes along with the direction of fill. That's not necessarily the case all the time with the inconsistent color mixing. It tends to be more just mottled and random in appearance when you have color mixing issues. Or you'll see the polymer separate from the colorant itself more at sharp bends in the part, so it might be lighter at areas of like a 90-degree turn of the flow path and what have you. So there's a few ways to distinguish between the two. But when you get the right color and polymer combination, they can look similar at times too. So I understand some of the hesitation.
All right, well, it looks like we got through all of the questions. So we would like to thank everyone for taking time out of your busy schedules to attend this Chase the Knowledge webinar. We hope it was informative and a great return on the investment of your time. If you have any technical questions that did not get answered today, feel free to reach out to Andrea directly. Her information should be posted on your screen there. But thank you all for attending, and we hope to see you at our next Chase the Knowledge webinar in June.